good evening, and good afternoon, and good morning, everyone. Thank you very much for this opportunity to introduce our activity in Patagonia today. My name is Shin Sugiyama from Institute of Low Temperature Science, the Hokkaido University in Japan. Do you know where is Hokkaido? Hokkaido is the northern island in Japan, and we are living in a city named Sapporo. Sapporo is the capital of the Hokkaido island. And have you been to Sapporo? So this is our city center in summertime. So it's surrounded by hills and mountains, and we have ocean on the other side. So this is our town. And now in December, we are getting snow in the city. So it looks like this. And soon, in a few weeks, in the mountain regions, we have a lot of snow. So if you like snow and winter activities, please think about Sapporo and Hokkaido for your next destination of holidays or maybe sabbatical. Today, I want to take you to an excursion to the other side of the world from Sapporo, that is Patagonia. Patagonian Ice Field is located at the southern end of Chile and Argentina, and many glaciers are distributed from north to south for 500 kilometers. Now, actually, the time difference between Patagonia and Japan is 12 hours, so it's really the other side of the world. So I think you may wonder why you guys in Japan are doing glaciers in Patagonia. It's so far away. So to address this question, I want to start with the history of Japanese glaciologists in Patagonia. So we go back to 1960s. In this 1960s, several mountain clubs of Japanese universities visited Patagonia for their glacier expedition. And one of those is from Hokkaido University. And this expedition is very important for me because one of them, Renji Naruse, he came back to Japan and started glacier research. And actually, he became my PhD supervisor afterwards. So this expedition and Renji is very important for me and for my talk today. Renji went to Glacier Sorel in 1967, but some others planned the traverse of the southern ice field. So they tried to cross this southern ice field at really critical part of the ice field. So if you know the region and also the weather in Patagonia, doing this in 1969 is something in between of ambitious and a bit of crazy. And they tell us a nice story at this Camp 10 at the middle of the ice field. In 1969, in February, they got stuck at Camp 10 with snowstorm, and the tent is going down, and actually snow is piling up. And this tent is naturally replaced by this snow pit. And after 10 days, they decided not to stay there anymore. And they were about 5 meters from the surface. But somehow they made it. They crossed the ice field and came back home. And one member, Shuji, he started glacier geomorphology, and recently he wrote a nice textbook of glacier in Japan. Then it took some 10 years. Those young mountain guides came together and to establish a new scientific research project in Patagonia. Renji was one of them, and Shuji was also there. So this was the initiation of Japanese glacial research in Patagonia in 1983. So it's about 40 years of history, and I am one of those who is following this tradition of Japanese glaciologists to do glaciers in Patagonia. Okay, so today my talk is on freshwater calving glaciers in Patagonia. I start with a brief introduction of glaciers in Patagonia. Then I want to show you today our result of the measurement in the lake and the glacier. The first one is the temperature and turbidity measurement, which showed very interesting thermal structure of lakes in front of the glaciers. And also we used side scan sonar and to see the ice geometry of the ice front in the lake water. And we also measured the lake temperature for more than a year to see its seasonal variation. So I want to show you this data tonight. The Patagonian ice field is characterized by many of outlet glaciers from the ice field. So it's flowing relatively fast to the west to the Chilean side and to the east for the Argentina. And these outlet glaciers, most of them are calving glaciers. And among those, actually more than half of the outlet glaciers are terminating in freshwater, lake calving glaciers. And these lake calving glaciers are doing an important role for the change of the glaciers in this region. If we look at the mass loss of the glaciers in Patagonia, and this red is the mass loss in Patagonia as compared to mountain glaciers in other regions. And in terms of specific mass balance, the change in the surface elevation, the Patagonia is the region where the glaciers are most rapidly losing mass. And if we see the total mass or volume of ice lost, it's next to Alaska. So glaciers, the mass loss of the glaciers in Patagonia is very important for the contribution of mountain glaciers to sea level rise. And if we look at the recent, the surface elevation change of Patagonian glaciers, many of the lake calving glaciers are losing mass, and these are names of the glaciers which are thinning at a rate greater than 1 meter per year. So such rapid mass loss in Patagonia are driven by these lake calving glaciers. And this Uppsala Glacier is one of those. Uppsala is a glacier with a width of 3 kilometers flowing into Brazo Uppsala, and ice is 600 meters thick and flowing at a rate of 2 kilometers per year. And this glacier is one of the most rapidly thinning glaciers in Patagonia. From 2008 to 2011, this glacier retreated more than 5 kilometers, and during this time period, the glacier was thinning at a rate more than 30 meters every year. So this is Uppsala as observed by De Agostini in 1928. So if you are there these days, you can see a nice lake like this. So this glacier has been retreating with interaction of ice and this lake water. In general, the glaciers ending in water, the calving glaciers, changes much more rapidly than glaciers terminating on land. So this is because there is an additional processes at the glacier front. There is calving and also melting in water. So these are additional ablation process of the glacier, and it makes it so complicated. And it's only recently, not only calving, and also this melting in water is very important for calving glaciers. Interaction of glaciers and ocean is intensively studied in Antarctica and also Greenland and Alaska, and they have some different mechanisms. And if you look at this Greenland, the tidewater glacier, it's very important to see this subglacial discharge. The meltwater goes to the bed and it goes out to the fjord from the bed of the glacier. And this discharge from the glacier is fresh water because it's meltwater, and it goes into sea water. So there's a huge density difference. And this fresh glacier discharge upwells to the surface. And when they make this plume in front of the glacier, it carries a lot of deep water, which is saline and also warm. And the heat of this deep water is transferred to this glacier front, and a lot of ice melt because of this turbulent plume. And in this case, the melting is more rapid near the glacier bed. So such upwelling of glacier discharge is a key process for tidewater glaciers. And the recent observation of multi-beam sonar shows actually the glacier front is undercutting. This is because the ice melts more near the glacier bed. And if there's undercutting like this, the ice near the front is getting more and more unstable, so it causes the calving. So discharge from tidewater glacier is important for melting in water and also for crevasses and calving. So now the question is, what happens if the glaciers are ending in fresh water, not the ocean, but fresh water? Is there any upwelling, or what kind of melting happens in the water? So is there any difference from tidewater glaciers? So this is my question today. This is Glacier Perito Moreno, and this was my first Patagonian glacier for field research. Some 10 years ago, I was there for hot water drilling to make a borehole somewhere around here. It was a very complicated operation, but I had a lot of time slowly drilling the glacier. And at that time, I was thinking about if this borehole, is this connected to the lake, or how the glaciers are interacting the lake water? So during this campaign, I was thinking about lake, the interaction with the lake, and getting more and more interested in the measurement near the front of the glacier. Then I talked to this idea to Masamu and Pedro. Masamu is one of those who initiated Japanese glacial research in Patagonia, and he invited me for this hot water drilling. He was a PI of that project. So without him, I didn't start the glacial research in Patagonia. And Pedro is an old friend of Masamu and the good collaborator in Argentina. They made a lot of study in Patagonian glaciers in Argentina. And I talked to them. I think the interaction of lake and glaciers, that's what we can do. So maybe we need a boat for that. They are very supportive, and Pedro did a lot of effort to find a boat and captain and made everything possible under difficult conditions. And this is a boat that Pedro prepared for us at Glacier Perito Moreno. The boat was a bit small, but we had a big twin engine on the boat. Daiki and Masahiro, they were graduate students of mine at that time, and they are very powerful. So with them, we could do a lot of measurement. And also, anytime we had very experienced the captain or guide in each glacier. So in this case, Maxi was handling all the things. He knows a lot about glaciers and the lakes. So he took care of everything about our measurement at Perito Moreno. So with Pedro and others, we visited 3 glaciers in Argentina: Perito Moreno, Uppsala, and Viedma. They are large glaciers flowing into big lakes in Argentina. So today I want to show you the data from Viedma. Viedma Glacier is the second largest glacier in southern ice field. And the glacier front is relatively narrow, 1.5 kilometers, but the ice is 400 meters thick and flows into Lago Viedma at a rate of 700 meters per year. We started with bathymetry measurement. So this contour shows the lake bed. And we found an over deepening in front of the glacier. Near the glacier, the lake is more than 400 meters deep, and then the bottom comes up, and at about 2 kilometers from the front, the lake is about 120 meters deep. So there is a sill at 2 kilometers from the glacier. And we made temperature and turbidity measurements at these 3 locations. I show you the data. So these are temperature in red, and the blue is suspended sediment concentration that we obtained from turbidity measurement. And this is near the glacier, and 2, 3, and this is the depth. So if we see this temperature, it's about 6 degrees near the surface, and there's a huge jump at 120 meters from the surface. And below this point, the water is very cold. Actually, it's very close to the pressure melting point. It was less than 0 degrees Celsius. And here, it's within a layer of 1 meter, the temperature changes more than 6 degrees. So it's really interesting and surprising temperature structure. And the reason why it shows such clear 2 layers is this suspended sediment concentration. The upper layer is relatively clear, but here the lower layer is very turbid. So it's turbid means it's dense. So we is the glacial discharge, the meltwater from the glacier, which is from the glacier bed, which is turbid, so it is dense, so it stays there. So we had essentially the same temperature and sediment concentration profiles at 2 and 3. This jump happens always at the same depth, at 120 meters from the surface. And I remind you, the bed there's over deepening here, and it's coming up to 120 meters here. So now I show you this map of the temperature on the vertical cross section. So you see there's a clear two-layer, warm and clean water for the upper 120 meters. And below that, the water is very cold and turbid, and it's dense. And at this 120 meters, this is controlled by the seal. So it looks the glacier discharge from the bed. It fills this basin until this cold water started the overtopping this seal. So this is very surprising result for me. Quite warm and clean surface water and cold and turbid deep water. So this is the thermal structure of the lake in front of freshwater calving glacier. When I saw this plot on my computer screen, by the way, I was very fascinated how it looks very similar to the best part of tuna fish. This underbelly of tuna is named toro in Japanese, and in Japan, this toro is regarded as the best meat of tuna. And if you go for Google search, you'll be confused. Where is fish and where is temperature profile? And I have a suggestion. If you visit us in Japan next time, go to a sushi restaurant and you can say, toro, please, so that you can get the best sushi in the restaurant. And also you can impress your sushi master. Anyway, this is what we observed. The two other lakes showed the similar result. So basically, the lake water temperature is formed by warm upper layer and cold bottom layer. And this cold bottom layer is due to the subglacial discharge, which is cold and turbid. And if there is a seal in front of the glacier, this seal controls the thickness of this cold layer. And if I see this, I'm getting more and more interested in what will be the influence of this lake temperature profile for the glacier melting, how the ice melts in the water, and how it looks like in the water, the ice geometry. So we decided to make another project, and there we are interested in the shape of the ice in water, and we want to see it by using side scan sonar. And we are also interested in the long-term measurement of lake temperature, so we prepared mooring devices. So our question was, what is the shape of the ice front in the lake? And also, what is the seasonal variations of the thermal structure of the lake? So this we did in 2016 to 18. And for this project, we went to the other side, to Chile. And there I worked with Marius from Valdivia. And actually, I met him in 2014 in Chamonix at IGS Symposium for the first time. And I met him. We chat a bit about Patagonian glaciers. And several months later, I invited him to Sapporo. And 2 years later, I came to Chile to work with him for this project. So I want to stress the importance of IGS meeting for us. So without that meeting, I couldn't do this measurement in glacier. So thanks for that. And this time our glacier was Grey Glacier. This glacier has 3 separated termini, and we went to this eastern terminus. The glacier front looks like this. The ice is about 1 kilometer wide, and ice above the water is 10 to 20 meters high. But this lake is deep. It's more than 200 meters. So quite thick ice is in the water. And this is our boat in front of the glacier. So 10 to 20 meters is still quite scary if we are there. And this boat we use, and what we did with this boat was operating this side scan sonar. Have you ever used this kind of device? This was my first time to use this side scan sonar. The device is usually used to map the floor of the ocean or lake. So it gets this kind of two-dimensional pictures of the floor using the reflection of sonic wave. But in our case, I was wondering if we can use this sideways beam direct on this glacier front, so that if we can illuminate or if we can obtain the shape of this ice in water. The point here is this sonar should be very close to the glacier front, otherwise we can't get reflection from the ice. So we are very close to the glacier front. I tried not to look at this side, focusing on the computer screen, and the captain and Marius were taking care of this side. So we did the best what we could do with this captain who knows a lot about this glacier. So I show you the image from this sonar. We operated our boat with a sonar along the glacier front like this. And this image, the center line is the track of our boat, and sonar collects data from right and left. And in this case, right-hand side, this signal is from the glacier front. So my interpretation is like this. There is a bright reflection here. So this is the signal within the lake water. And there is a boundary of signal and no signal. And this boundary corresponds to the ice front at the water surface. There's no reflection further because there should be no reflection from above the water. So if you look at this, it looks the ice is sticking out from the glacier front into the lake. So this is the same sonar image, but now it's projected to a real space and combined with the satellite image. This white dashed line shows the ice front from the satellite image. And this light blue is the ice front at water surface as observed by side scan sonar. And this red is this edge of ice within the water. And this map shows there is a kind of terrace of ice in the water, and the length of this terrace is 30 meters in average across the glacier. And the distance from the water surface to the terrace is about 50 meters in this case. So this is what we observed, and this geometry was confirmed by a local guide, mountain guide Tadeo. Tadeo helped us a lot for this side scan sonar measurement. And after the measurement, he wrote us email that he observed the very interesting carving. It was about 9 months after our side scan sonar measurement. The ice was lifting up, and this white part is ice above the water. And now we are seeing this blue ice, which is coming up from the water. So it looks, the ice is really sticking out from the ice front into the lake, as we observed by the side scan sonar. And Tadeo took a movie afterwards. Now the carving ice is turning around to the other side. And now here, the lower part of the ice is coming up. So this film tells us this carving thing. So probably the full depth ice was floating up because of the buoyancy acting on ice in the water. So our measurement of side scan sonar was done in this February 2016. It was, the front was like this. And this ice showed a big carving in October. And after the carving, the glacier front is like this. So what do you think? After the carving, do you think there is still ice terrace underneath? So we had a chance to visit the glacier once again in 2017, some 4 or 5 months after that carving event. And this is the side scan sonar image in 2017, 130 days after that carving. And again, we still see this red line is a bit in front of the glacier front as observed by satellite image. So there is still ice terrace, which has a mean length of 26 meters. So ice terrace forms relatively quickly after the carving event. So the reason why such an ice terrace is formed is temperature profile. So we made temperature measurement of the lake. The red is water temperature and blue is turbidity. So again, the near surface, upper 50 meters have relatively warm water, and below the water is cold and also turbid. So it's essentially the same, the thermal structure as Viedma, and this near surface warm water was eroding this part of the glacier, and this lower part was floating up during the carving event. So our side scan sonar measurement showed there is an ice terrace about 50 meters from the water surface. And this kind of geometry was formed because of the warm surface water layer and cold deep water. So there is a difference in melt rate. And such ice protruding into lake causes a big underwater carving event. So such carving should be important as an ablation process for freshwater carving glaciers. And it's not only at Grey. So this is a film filmed by my colleagues at Viedma. The ice is popping up in front of the glacier. And in a few minutes, more and more ice blocks are popping up from the lake, and see there's no change at the glacier front in the air. So all these are coming up from within the lake. And please also look at this turbid water coming up with this ice. So this is, we believe, very cold and turbid meltwater discharge, which filled the deeper part of the lake. Okay, so now we see the ice front in the water, and we know which is caused by this temperature structure. So my next question is, what is the seasonal evolution of this lake water temperature? So we did a mooring measurement in 2017 to 18. In this case, we moved to the central glacier front because the lake is deeper there, more than 400 meters, and it's more along the glacier center line, so that we can expect more glacier discharge into the lake. So first, I want to show you the temperature data at these three locations, and our mooring measurement is somewhere around here. So this is the temperature and turbidity profiles that we measured in summer. So it's always near the surface, the temperature is high, and it drops to the lower region, and the turbidity increases in the deeper region. So about 100 meters thick warm layer, and below there's a cold and turbid layer. So now we see the seasonal variation of these thermal conditions. So we set 5 temperature sensors at about 1 kilometer from the lake, about 400 meters. This was my first time to this kind of long-term measurements in water. So I asked my colleagues, oceanographers, to know what we can do for such measurement. I talked to my friend Yasushi in Sapporo. He is an oceanographer, and he designed this instrument for us. Basically, there is a big float at the top of the stream, and there are sensors in between. And the lower end, there is an acoustic releaser, which is connected to a sandbag. So it's relatively simple. We throw this in to the lake, and after a year, we go there and push a button to send an acoustic signal. Then this releaser will open this connection so that everything pops up except for this sandbag. I also learned from Fiamma when she visited Sapporo in 2015. So the oceanographers, encouraged me very much. So this is the installation in 2017. We throw everything into the lake. And after 1.5 years, we are very lucky to get everything. And I tell you, it's not always like this. After this recovery, we brought all the instruments to Uppsala and throw it in. And we were there in March this year, pushed the button, nothing happened. So the instruments are still in the lake of Uppsala, so that it's not always such successful. This show you the data from this mooring measurement. This is a plot of temperatures measured at these 5 different locations. This is time for about 1.5 years, and the temperature blue is the near surface. So let's look at this blue. So temperature drops in winter time and it comes up in summertime. So this is what we expect, very similar to the air temperature change. But for the next sensor, the green, it follows with blue, but in December, it drops. And it shows the coldest temperature of the year in January, the mid of austral summer, the water was the coldest. And for the lower sensors, actually they reacted earlier. In October, the temperature dropped and going down and showed the coldest temperature in January when the glacier was melting a lot. So we expect the glacier discharge during summertime was affecting this deeper part and later this mid layer. I look at a bit details of this temperature drop here. So this is the October to the left and January to the right. And the upper panel is the temperature in air temperature in red, and black is the precipitation. So this is the data from Christoph Schneider and Tobias Sauter from AWS, the weather station in Grey. And the lower panel shows the lake water temperature. In October, the lowermost sensors show drop in temperature, and it looks it was caused by this rain event. Probably a lot of rain goes into the bed and caused the discharge in early spring, and this influenced this temperature at the deeper part of the lake. And in January, this second sensor dropped in temperature. And before that, there is a period of high temperature. So there must be a melt event. So I assume this melt water from the glacier was piling up from the bottom and somewhere influenced this second sensor, and that was in January. So this is the same data set, but the plotted now for time in X, but this Y is for the lake depth. Near the surface, the temperature is going up in October, but exactly at the time, the deepest part started the drop of the temperature, and this cold layer at the bottom getting thicker and thicker, and at the mid of the summer, it reaches to some 200 to 250 meters thick. So this is the change in the thermal structure of the lake, and I believe it's very important for the melting of the glacier front in the lake, and also for the calving, because the geometry of the ice influences a large underwater calving event. Okay, so let me sum up my talk. Our measurement at freshwater calving glaciers in Patagonia told us that there is interesting thermal structure. Very cold and turbid meltwater stays at the deeper part of the lake, and this is very important for the melting for the glacier front. And because of this thermal structure, ice melts more near the water surface, then ice gets sticking out at the deeper part of the lake, and it feels buoyancy, and sometimes this causes a large underwater calving event. So this is an important ablation process of lake terminating glacier. And this temperature structure of the lake change in season. And actually in summertime, the lake water gets colder, especially at the deeper part. And this thickness of the cold layer getting thicker and at the maximum in the mid of the melt season. So I would say the glacier discharge influences the lake water temperature structure, and this lake water causes a change in the melting of the glacier front. And ice melting in the water causes big underwater calving. So glacier discharge is important for ice melting and also calving, also in this freshwater calving glacier, but in a bit different way from tidewater glaciers in Greenland and in Alaska. Okay, now I come to the final slide of my talk. So next time when you go to Patagonia, please visit the freshwater calving glaciers and imagine there is a terrace of ice about 50 meters from the surface, and there may be the IGS band is playing music for us. So this is another secret of Patagonian freshwater calving glacier. Thank you very much. This is and I show you one more slide. So this is for the talk next week by Agneta. Glacial water matters for the seawater and sea ice carbonate chemistry, carbon dioxide fluxes, and ice acidification in Svalbard fjords. So good luck, Agneta, for your talk. Thank you very much. Thanks, David.
Well, thank you very much. That was fantastic. Really, really fascinating to see the difference between freshwater calving and typical Greenland fjords, for example. Are there any questions for Shin at all? Oh, Roger, go ahead.
Yes, thanks very much, Shin. Really enjoyed that.
Hi. Thank you.
And as I said last week, excuse a naive question from a confused seismologist who's meandered into the meeting. But I really enjoyed seeing all those temperature depth profiles, especially the first ones with that incredibly sharp boundary. And I wondered whether or not you'd seen any expression of that in your side scan sonar acoustic measurements, because there'd be quite a significant reflection effect, I would imagine.
Exactly. We see a lot of reflection from this 120 meters deep, the change in temperature. So first, we didn't know what we are seeing. And also we see a strange reflection near the bottom, some places. So I'm afraid there might be some ice left at the bottom without melting. So this kind of reflection of sonar was very a bit confusing for us. So it took for a while to explain that. Yeah, as you said, so it's a very complicated reflection.
Smashing. Thanks very much once again.
Thank you. Thank you for the question.
Pete Nino, are you?
Yeah. Hi, Shin.
Hi,
thanks very much. That was a fantastic talk.
Thank you.
Just in terms of the lake observations, have you got any idea what circulation patterns there are in the lake? Because obviously the density differences are very different compared with in Greenland. So the subglacial discharge isn't buoyant, but we also know that in terms of the sort of submarine melt, it's controlled by both temperature and the velocity of water. So I just wonder if you've got any sense of what the circulation pattern might look like, either from observations or modeling or a hunch.
I see. Yeah, it's a bit dependent on the geometry of glacier and the lake. As I show you here, basically this cold and turbid water goes to the lower part. But if there is a bed geometry like this influences the thickness of this cold layer. And for the upper part, the Patagonia, there's a lot of radiation, so it's a warm water, and it may be circulated because of this wind. So for some glaciers, we see such clear two different structures. One is controlled by this bed, and this thickness of upper layer is also influenced by wind strength. When the wind is strong, it mixes, and it sometimes go down to 200 meters. So it depends on this atmospheric condition and also the basal geometry. So that's what is in my mind about circulation of water in the lake.
And can I just add, and do you have any idea, I mean, is it fast circulation, or is it really just dominated by the temperature, the melt, do you think?
I would say I don't know, but it also depends on the lake. If the lake is small, the usual circulation is not so active. But for Viedma and Uppsala, the lake is big. So such big lake causes more circulation, I think. So that's what I can answer to your question.
Brilliant, lovely, thank you, it was great.
Thank you, Pete.
And Paco, you have a question.
Hi,
Okay.
Paco.
Hello,
Good evening.
nice to see you, and really nice talk. I enjoyed.
Thank
I
you.
just wonder whether you did any velocity measurements during any of this field work. Velocity measurements from the
You
glacier.
mean
Did you in any case do simultaneous velocity measurements? And did you observe? If so, did you observe any strong increase after these heavy rain events or strong melting? And could this have some influence on this, also this calving you observed?
I see. I don't have ice speed measurement during our mooring measurement. But that's what I want to see by using satellite image. But at this moment, I don't know if the glacier was accelerated during this period. That's a good point.
Okay, thanks.
Thank you, Paco.
Celia Martin?
Yeah, I'm here.
Hello.
I wondered if you saw any convection due to the 4-degree temperature maximum in the fresh water.
No, the convection or the water movement is controlled by the sediment concentration. It's so turbid, so the temperature doesn't do anything about the density. Density is controlled by sediment concentration. So it's always turbid water, the bottom, and clean water up.
Okay, thank you very much.
Thank you for the question.
Tim, are you there?
Hi, Tim. Oh, you have to
Oh, you're still muted, Tim.
unmute.
Got it. Great to see you,
Hi,
Shin.
Tim.
Thank you for your talk. I
Thank
appreciate
you.
your hints and bills there. I was wondering, I missed, my understanding from the side scan sonar is that it only tells you sort of what the two-way travel time is, and then you have to infer from the travel time where it's actually reflecting from. And so I was wondering, when you're trying to interpret those shapes of the sublacustrine glacier face, how you knew where what was reflecting off near the water line and what was reflecting off near the bottom.
Yeah, you
because it seems like you could get the same kind of data either with major terraces or with kind of undercuts.
Yeah, you're absolutely right. So side scan sonar cannot distinguish from where the reflection come from. So we get this image, but we need some imagination. So my interpretation was like this, and we are not sure if this is true. So we are sure when we went close to the glacier, and we are doing CTD measurement. And when Masahiro found the CTD device stuck somewhere 50 or 60 meters at every places. So we realized we are on or above the ice sticking out. That was the point we reached. The ice geometry was like this. And of course, that observation of the mountain guide, that was the evidence of our interpretation of the sonar. But you are right, side scan sonar gives image, but we need imagination for the interpretation.
Gotcha. Excellent. Well, I'm glad you're safe.
Thank you, Tim.
Beatrice.
Great talk. I really enjoyed it. So we're working with Pedro down in Patagonia, and we're working on Uppsala. We just collected 350 kilometers of chirp and seismic reflection data. And so we also collected cores, and so we're going to be looking at the sediments and the structures of the sediments, both the moraines and the drift. So and I read your paper about the turbidity, and I need to go look at the 2019 paper now. Thank you for giving these talks. So one of the question I had is, you're assuming that the glaciers are grounded, that the ice goes all the way to the bottom. Do you have any evidence that they might become ungrounded?
Yes, I would say yes. Maybe. Yeah, for example, this is a front of the eastern front of Grey, and ice is relatively thin above the water. And we know from the sonar measurement, the lake is more than 200 meters or sometimes 300 meters deep. And this 10 to 20 meters doesn't fit to this lake depth as a grounded glacier. So as the glacier is thinning, I suspect the front is gradually lifting up from the bed. But I guess it doesn't stay like that so long. It causes calving soon after. But I suppose some part of the ice front is a bit floating.
I think we have a question from Andre Rivera as well.
Yeah,
Andre.
Thanks a lot. Yes, thanks a lot,
Nice
Shin, for your talk. It is a privilege for us to have you and your team working in Chile and Argentina. I have a question for you regarding the role of the precipitation in the drop of the deep water that you measure. I'm not sure if the temperature of the precipitation is the right one for reducing this deep water temperature. How is the connection between the precipitation and the drop of the deep water?
I see. Excuse me for confusing you. I mean, this rain not go directly into the lake, but the rain falls on the glacier and then went to the glacier bed. And it's supplied as a subglacial discharge into the lake, and that goes to the deeper part of the lake. That's why only the deeper sensors reacted for this rain event. That's my interpretation.
Okay, well, thanks.
Thank you, Andre.
Yeah, cheers.
I think we're at the end of the questions there, but we have some comments from various people back and forth in the chat. So unless there are any further questions, I think it comes to say thank you very much indeed, Shin, for a fabulous talk. It's been really wonderful and great discussion. Thank you everyone for coming. I will send you actually a copy of the chat, because there are so many people just saying thank you for a great talk. So that's nice.
Wonderful. Thank you.
So thank you very much to everyone for coming, and see you next week for Agnata's seminar. But thank you very much again, Shin. It was really
thank
fabulous.
You, Debbie. And thank you, everyone.
Okay.
I got all my screenshots.
Thank you, Doug. Nice to see you.
Good to see you. And it was a great talk.
Thank you.
Doug, did you get the stuff I sent?
Yes, I did. Thank you.
Brilliant. Okay, see everyone next time. Cheers then. Bye.
Bye, Magnus.
Thanks again.